Next, we're going to talk about confidence intervals, a topic that again should be a reasonable review for those of you who took Data 8, and I do encourage you to go back and revisit the Data 8 textbook for a really good intro. So intuitively, what a confidence interval is a way of conveying where do we think the true population parameter is based on both the value and the variance of our estimator. Now, specifically, what does a p% confidence interval mean? Imagine that this is really all about a process. Imagine that you could do the following. You could take a sample from the population. Somehow you have a process for saying, based on this sample, my estimated parameter has this value, and this is my p% confidence interval for that value. Now, how do you produce that interval? For now, we're going to leave it unspecified. Somehow you can do that. You can say, given this value, this is the error bar around it, and that error bar is a 95% confidence interval. We often use 95%, but you can pick any value, p%, right? The idea is that if you say this is a p% confidence interval, if you could repeat the process many times, meaning if you could keep resampling, which we can't, right? But if you could keep resampling, and every time you produced a p% confidence interval for each estimate, that in the long run, if you did that infinitely many times, in the long run, p% of the time, your answer would be correct, meaning your confidence interval would contain it, which means you're allowed to fail. An 80% confidence interval, 20% of the time in the long run, would not have, 20% of those intervals would not contain the right answer. Some of them might be quite far off. So it doesn't mean, so confidence intervals are sort of allowed to fail. They do not necessarily capture the true value, but they are based on this procedure, and this is how they convey your uncertainty about your estimate. Now, how do we construct in general confidence intervals? We're not talking about the Bootstrap process, just in general. We assume that we have a function f, which is an estimator that guesses the value of the parameter theta star that we would like to know about our population, which we don't have access to. And so if we have our population, we draw a sample and we keep sampling. This is, again, we're not talking about bootstraps, we're talking about the concept of confidence intervals. So we're assuming that given our population, we could take as many samples as we would like. And so the idea is that given a function f to estimate our parameter, and given a value p, our confidence value, a function ci would take the sample we have, the estimator, and the value that we want of p, and it would produce an interval. It would say, this is the value for the estimator, and it has the following confidence interval. And we do that again for each of the samples. And so each time we end up with a different interval, right? They're going to be, the samples are different, so the actual value of the interval is going to be a little bit different. Now, in the true population, right, there is a true value of theta star, right, which is somewhere. Right, that value is what it is. We have no access to it. We have no way of knowing it, but it exists, right? And so the point is that on average, p% of these, if we could do this infinitely many times, would include theta star. So for example, a few of them, if p is say 95%, 5% of them might be off, but roughly 95% of them should include the true value. Now the question is, how do we compute this confidence interval? So what we want is a way of approximating the sampling distribution of f using the sample s, right? And then we will pick the middle p% of samples from this distribution. This is one simple way of computing confidence intervals by using percentiles, right? Which is if we find a way of having the sampling distribution of f, which in this case, if we could keep drawing samples, we could do so, right? Then by finding the middle p% of the samples from this distribution, we end up with a percentile-based confidence interval. Now, the problem is obviously how do we get the sampling distribution of f? Well, in general, we would like to sample from the population. We can't, and now we get to the Bootstrap. So the next part of of this process should now come pretty intuitively to you that, well, instead of having many samples, we have our sample, we follow our Bootstrap resampling process, and this will give us an approximation to that sampling distribution that we're after, right? Because from our one sample, our Bootstrap samples, let us compute F, right? Based on these values, right? Now we have estimates for each of our Bootstrap samples of our value, so we can now construct a distribution. This is our Bootstrap distribution, the distribution that we've been seeing. So we can say, well, give me the middle p% of this value. If I draw a histogram of all of these values, the middle p% of these will be my confidence interval. And so it is a pretty straightforward process to go from the general idea of a confidence interval, which is an abstract one, into this concrete implementation based on the Bootstrap method, which is actually quite straightforward. And if we look at the code, if we look at the code looks actually very, very straightforward. This is a complete implementation of a confidence interval. So given a sample, given an estimator, what we call F, a confidence level, which often defaults to 95, then we actually go ahead and grab each of our samples, right? And then we compute our estimate. So we do our Bootstrap resampling, we compute our estimator. Our estimator is our function right here. So we compute our estimator on this resample and we store it. And now that we have these estimates, NumPy knows how to find percentiles. So all we need to do is find that middle. And so let's say that our confidence was 95. We can define, basically we're looking for if we're talking about a 95% confidence interval, what we want to find is what's the middle 95%, which means we want the remaining 5% to be 2.5 on the left and 2.5 on the right. Let's call that the slack. So it's 100 minus the confidence level. And then the lower interval is half of that. The percentile, in this case, it would be 2.5. And the upper limit will be 100 minus that, so 97.5. Those are the two points at the edges. And we return these 2 points. So it's a pretty straightforward implementation of what we just described. So this is an example for our sample 100 interval and using the mean of what the confidence interval would be. In this case, the confidence interval goes from 4580 or so to 5670. It does include 5000. So from our sample, which let me remind you, this particular sample of 100 has a mean of 5100. It's not the true mean, which is 5000, but the 95% confidence interval drawn from this sample does include the true answer. Now here, we can look at the Bootstrap distribution for this sample. And this is what we had already seen before, so this is just reiterating what we did in the last plot. We see that this distribution is centered around 5100, but the 95% confidence interval is basically looking at the keeping the 2.5% of the samples on the left and 2.5% of the samples on the right, and keeping 95% of the mass of this histogram. That is what goes from 4585 to 5670. So from 4585 would be around here to 5670, somewhere around here, give or take, right? That is the 95% confidence interval based on this particular sample. Now, what about this notion of the interpretation of 95% confidence intervals, right? As we said, it doesn't mean it's about the process, right? What we're saying is if we could do this by drawing from the original population thousands of times, on average, in the long run, 95% of them, of the times, we expect to get the true population parameter included within our confidence intervals. So let's actually do this. Let's compute this for by going back to the true population, which in this case we do have, and constructing 100 times. So we're taking samples of 100, but we're doing that 100 times. These 200 are different. This is the sample size. So we're doing samples of 100 for which we're computing the mean, but we're going to compute 100 of them. We have a little progress bar showing us here what these means are. And so it finished. Let's take a look at the first few of these. Let's say the first 5. So these all seem to contain the true answer. So in the first 5, the true answer is always contained. We could look at a long list of numbers, but let's actually visualize this with a little bit of code, where what we're doing is we are drawing each of the confidence intervals in blue, unless it doesn't contain the true mean. The true mean is 5,000, which is drawn here with an orange line. So in this case, there are 1, 2, 3, 4, 5 that are not. In this case, we got exactly 5 out of the 100 that do not contain the true answer. So this could have been the one that you got in your given sample, which means your 95% confidence interval would not include the true answer. That can happen, right? But if we do it 100 times, in this case, we see how we actually got 95% of the time we did get the true answer. Now, if you run this again, I'm going to do it once more to see what happens, just to show you that it's not guaranteed to be exactly 95% of the time. But I don't know, I might get again 95. And I'm not going to do this many times. Earlier today when I ran this code, I got an example where I got, for example, 91% of them. You could get 97%. We'll see what happens if we do it one more time. But it takes long enough to do this that I'm not going to do it too many times. So let's see, in this case, all of the first 5 still do include the true answer, but let's see, well, 94%. So in this case, we got one more. So at least it does show you that there is some variability here, and obviously the ones that don't contain the right answer are different from the ones at the beginning. So hopefully this illustrates to you that it is actually a fairly straightforward process, but it also illustrates this interpretation, right? It's not the case that a 95% confidence interval means there's a probability that the population parameter is in our interval, because there's no probabilities left in here. There's no randomness left. The population parameter was a fixed number. In the case of our toy example, it's the mean of numbers from 0 to 10,000. It's 5,000. That's it. That number is fixed. Our interval is also fixed. Once we have a sample, we produce both an estimate for the mean and an estimate for the confidence interval, and either that number includes the true mean or it doesn't. Either our little bar is blue or red, and that's the end of it. There's no randomness. So the interpretation of the 95 confidence interval is only in the process to build these. So it's basically in the fact that if you can build this graph, then all of these will have that distribution of roughly p% of them capturing the true answer. But we only do this to illustrate for you what the underlying interpretation is. But in the real world, you will have one of these. And so you need to be mindful of sort of the picture that should be in the back of your head when you quote to your colleagues, when you write your paper, when you quote to your boss one of these numbers. You could have a blue bar, or you could have one of the red bars, and you don't know. There are other ways of computing confidence intervals. We've used a method called the percentile bootstrap confidence interval, but you could make assumptions, for example, about the sampling distribution of your estimator and use that to build confidence intervals in a different way. Now, finally, I want to mention that the notebook contains the construction of confidence intervals for other quantities like the median or the standard deviation or a high percentile. I encourage you to play with it, but to remember, and you can go back to the link, the discussion that we have in that paper by Hesterberg about the fact that for some of these quantities, the results can be a little bit trickier to deal with. So I do encourage you to play a little bit with the code and go back to that paper for more discussion.